So, hi and welcome to lecture 25 on convex analysis. And today in this lecture we come back to the analysis and development of algorithms to solve optimization problems. So now we're in the realm of monotone operators, and so we're gonna write or develop algorithms for monotone inclusions instead of convex optimization problems. As we've seen, every convex optimization problem is also a monotone inclusion for the subgradient, but the class of monotone inclusion is slightly larger. Slightly, I don't know, but it's larger. So what we're doing here applies to all convex optimization problems, but even to a little larger class. Okay, so the chapter is 25, relaxed Mann iterations. And so what this is about is it's basically an extension of the Banach fixed point theorem, which works without contraction. Okay, so and before we state these iterations and prove convergence, we introduce a notion which is pretty helpful in this context. So this is definition 25.1. It's the notion of Fee monotonicity. So we again work, we still work in X, which is a finite dimensional Hilbert space, actually a real one. So basically equivalent or isomorphic to Rn with some inner product, but so we don't need that here. So we need so the notion that we need is if we have C is a non-empty subset of our X, then we say a sequence Xn in X is called Fee monotone. How does this work? It goes like this: Fee monotone with respect to C if the following holds. For all X and C, it holds that the next element in the sequence is closer to the current one. So if this here is our C, then a Fee monotone sequence here, this is our Xn, it should be, so the next Xn plus 1 should be anywhere such that it's closer to all the points here, and this can be visualized somehow. So if you project this Xn onto C and then draw the separating hyperplane, then everything which sits here fulfills this closeness here. So it's closer to all the points. Actually, that's not true, I guess. Sorry, I was wrong. No, that's not true. That's not true. So, but yes, I have to think about the picture for this. I didn't prepare, and I'm not sure. Of course, there are notions where this is where this xn plus 1 still has a lot of freedom where it can lie. Okay, so the smaller the C, the more freedom you had, but I refrained from doing a complete picture because it may be misleading. Okay, so it kind of has to move closer to all the points in C. And for example, if C is just 1 point, then there's still a lot of freedom. Everything in full ball. A full ball around that point. So, but now the importance comes not from the graphical interpretation, but from the immediate consequences. So the consequences are 25.2, our proposition. So if again C is a subset of X, C is not empty, and Xn is Fee monotone with respect to C, then it holds. Then you have a lot of consequences. One is then the sequence Xn is bounded and hence has a convergent subsequence, which is also nice. For every X in C, it holds that the sequence Xn minus X converges as a, so it's a sequence of real numbers. It converges. We don't say to what it does it converge, but it does converge. It's not diverging. Third condition is the distance of Xn to C is decreasing and convergent. as well. And last thing is for all m and n, it holds that the distance of xn plus m minus xn is smaller than 2 times the distance of xn to c. Okay. Good. So let's prove these. This proposition, it's fairly straightforward. So this first one is pretty clear because you have that xn minus x is smaller equal x0 minus x. And so you see that the distances to x are all bounded, and this means that the xn's are bounded. So if you want to have an intermediate step, you could first say that xn minus x is bounded, but x is fixed, then xn is bounded as well. Okay, so the second point is even simpler, because this here is decreasing. Not strictly so, but it's decreasing. And bounded from below, and that's it. Yeah, it's decreasing and bounded from below, hence convergent. Okay, that is also straightforward. For 3, let's just write down what does that mean. What is this distance here? So this distance of the next element in the sequence is the infimum over x and c over the norms of xn plus 1 minus x. And that's of course, let's say, take a y here and use a y. And then this is for any x and c, you can just estimate it from above by plugging in one special thing. So this is the infimum over all y, so we just plug in something special. And now we know that this xn is Fourier monotone, so we can estimate like that. And now we take the infimum over all the x's and c, and we're done. Infimum over x and c proves 3, because the left hand side does not depend on the x. Okay, and for the fourth, it's just the triangle inequality. So if you have xn plus m minus xn smaller equal xn plus m minus x plus xn minus x, and then Fourier monotonicity shows us it's smaller than 2 times xn minus x, and then again the infimum over x and c proves number 4. That's already it. So that was pretty straightforward. Okay, that's the notion of Fourier monotonicity. So if you have some set and move and then a sequence which moves closer to all the elements in the set, then you know that the sequence has to be bounded. The distance to any set, any element in the set does converge, not necessarily to 0, but it does converge. So as well does as the distance to the full set does, and then you have this estimate on the distance between two following iterates, two distance iterates somewhere in the end of the sequence. Okay, good. So before we come to the algorithm, there's one more notion here. That's just the notion of fixed point set. That's pretty, you know that already, I guess. But because it's notation, let's define it. So if we have X just some set, not necessarily Hilbert space, and T mapping the space into itself, then we say fix of T is the set of fixed points. So this is all X in X such that Tx is again X. So it's a set of fixed points of T. Okay, good. So, and now Mann iterations are, I don't know what, sometimes they're called Mann iterations in the context of monotone operators, in another context sometimes they're called Picard iterations, sometimes they're called Banach iterations. So it's just the fixed point iteration for some T. So just an iteration like this, you have some T and you just apply this T to some xn, get the next xn plus 1 and do that all over again. So that's what here in this collection now is called Mann iteration. Okay, what you know is, so if T is a contraction, So Lipschitz constant smaller 1, then xn converges to a fixed point by Banach's theorem. So that's stuff you've probably learned in analysis 2 when it comes to a Picard iteration for ODEs, or even earlier when it comes to the inverse function theorem, implicit function theorem. So but we could also use it here to solve monotone inclusions somehow, and we're going to do that. So but the thing is, in our context here, most of these operators T, which you can construct and will be helpful for algorithms, they are not contractions, they are merely non-expansive. So that's one thing, but if T is non-expansive, so Lipschitz constant, well, technically smaller or equal to 1, but of course the interesting thing is if it's equal 1. Then convergence of xn is not true in general. And of course, simple example is T is minus the identity, right? If T is minus the identity on a Hilbert space, then it just flips an element around the origin back and forth, and then you will never see convergence to any of the fixed points. But of course, there is a fixed point in the middle, right? So here's our origin, and then this here is xn, then xn plus 1 would be here, and xn plus 2 would be there again, and you will never converge, although there is a fixed point right in the middle. Okay, good. Okay, so now we come to the theorem which states that under just one simple additional condition, which we will be able to show afterwards for a practical case, that this iteration is still converging even if T is non-expansive. So this is theorem 25.4, and this has a complicated name, so it goes under the name Mann, but also Krasnozelski. So in the lecture notes I tried to write down the better transcription, but for here this would be enough. And the other name is Mann. So the Krasnozelski-Mann fixed point theorem. Okay, so you need a D subset of X, and of course not empty, closed and convex, and T should map D into D non-expansive. Okay, and fixed T should be non-empty, so there should be a fixed point at least. At least one fixed point is enough for that theorem. Okay, and then for some x0 and d, we define the sequent xn plus 1 equal to txn, so just the fixed point iteration. And then the statement is if it holds that xn minus txn goes to 0 for n to infinity. So the distance between xn and xn plus 1 here goes to 0. Then xn converges to some fixed point. Of t. So that's the additional condition. So if you do the simple fixed point iteration for some non-expansive t, you will not have conversion in general, but if you know that the distance of x and txn goes to 0 as well, then you have convergence towards a fixed point and nothing else. This condition here has a name. It's called that the xn is then called asymptotically regular. Asymptotically regular. So I'm not sure if I'm going to use that, but that's a common name for that. Okay. Good. Now let's prove that. So contraction arguments cannot work, and of course, and moreover, it's highly unlikely that we will get something on a rate or an error estimate because we don't have anything in hand here. So we only have non-expansiveness, and this will not be enough for anything. Okay, so what we do is we take some x in the fixed point set. So we take some fixed point because we know there is one. And then we know that xn plus 1 minus x, it's actually the same as txn minus, and then x is equal to tx because it's a fixed point. Okay, so we just used the iteration here, and that x is a fixed point, and now we use non-expansiveness and know that this is smaller than xn minus x because t is non-expansive. So, and this shows already that the sequence xn is Fourier monotone with respect to the fixed point set, right? Because this works for all the fixed points. Nice. Okay, good. And then we can just, from the previous proposition, we know that xn has cluster point. So xn bounded and hence has cluster points. Okay, so that's good. We take one. So what we do is we take a subsequence x and k, which converges to some which we call x star, k to infinity. Okay, that's always nice if you talk about optimization algorithms in our context here, where we do kind of low-cost optimization thing, just doing very, very simple steps, nothing complicated, no solving systems or stuff like that, or having anything intricate happening with the x, just doing a simple application of the t. It's often the case that we can first conclude boundedness. From boundedness we have conversion of a subsequence to something, and then we upgrade these results step by step to showing that this should be a fixed point, and then also the full sequence should converge. Okay, and this is what we do now. Okay, so how we do it. So we know that we start kind of arbitrary at this here, x star minus t of x star, because we want to show that x star is indeed the fixed point. So we want to show that this is 0. Because then we would have that at least a subsequence converge to something that we want. So up to now we don't know what the x star could be. It could be anything. Okay, but here comes the thing. Let me check. This was a kind of unintuitive thing. What we did is... yeah, okay, I just write it down because it's a little bit non-obvious, and then I explain. So it's equal to xn minus t of x star, and of course the t could also could not be gone, minus xn minus x star squared minus 2 times xn minus x star, and then here we have x star minus t of x star. And you see, if we bring these two things to the left-hand side and revert the binomial, or put the binomial together, you see that the x star is going to cancel and you get exactly this. So this is just an expansion of the quadratic. So we take xn, you take xn minus tx star, and you add and subtract x star, and then open up expand the quadratic, and you rearrange to this. Okay, so we rearrange a little further, still do not estimating anything by, let me check, how was that? We introduce here in this term t of xn. So xn minus t of xn. So by adding and subtracting it, so we get an additional plus 2 times xn minus t of xn, t of xn minus t of x star, or there's some more rearrangement going on, let me check afterwards. Then there's plus t of xn minus t of x star. No, that's exactly what you wanted to have. And this is still subtracted, xn minus x star squared, and we also have this negative product, xn minus x star minus t of x star. Okay, so and now what do we get? Let me check. Hopefully there's nothing broken with the factors here. just had a look yesterday, but it's okay. So what you get is these two terms here. By non-expansiveness, or maybe I should have highlighted them in some other color. So this term here and this term here, we could eliminate this because we add less than we subtract, right? Because this is t is non-expansive, this is at most this here, so we can just eliminate it. And I think there's indeed a factor of 2 missing. Because now we estimate by xn minus txn squared plus the 2 inner products here. Yeah, 2 inner products. Xn minus txn and txn minus tx star. This was plus minus 2 xn minus x star minus tx star. Okay. Maybe I was a little bit too quick here on the proof, because I think now I see that something. Yeah, I was a little bit too quick. Inviting that down in the lecture notes. I think I want to expand it, so let me explain. So first, we know by Fee monotonicity that this guy here goes to 0. And the same holds here, so this I don't care about, this is bounded anyway, but this here goes to 0, so this guy goes to 0 as well by Fee monotonicity. And here it's not so obvious because this is the longest subsequence. Here we only know that the x and k converges to x star, but not the xn converges to x star. But we also have by Fee monotonicity that these, so this guy, by Fee monotonicity we, let me get it back. So we know that this is converging to 0, no, it's converging, but this is bounded by that. So these things, yeah, so, yeah, should I, it's a little bit different, so let me try once again. So what this we already have. Also, we know that, that dxn fixed t converges, but no, sorry. Sorry. So I missed some point. So I don't have the thing in the right order here. So this is we also have to prove that this is going to vanish, and that is. I just missed it here, why this should follow right now already, because we only have it along a subsequence here. So it's not necessarily true that this vanishes at all, but if we would show that, so let's assume we showed that, and I'm going to upload the solution later on, then this would show that x star is in the fixed point of t. Okay, but then if we have that, let's assume that we have that here. So this is now, I need to fix that. So but now we have that xn converges towards the fixed point set by proposition 23, 25, 3, 3. But since we also have that the subsequence here, along the subsequence, you converge to x star, which is in the fixed point set, we know that the full sequence has to converge to the fixed point set as well. So it does converge to something. Along one sequence it converges to 0, so it has to converge, the full sequence here has to converge to 0. And that was the proof. And there was this gap here. I did not check why this guy here does converge along the full sequence and not the subsequence. I guess that's simple, but I just missed it here, unfortunately. Oh, yeah. Okay, I'm going to fix that. Okay. Good, but no matter what, the theorem here is indeed true. This additional assumption here, asymptotic regularity, ensures that even non-expansive iterations does converge towards fixed points. Okay, and now let's come to the main theorem. It's the first main theorem here on the iteration. So, and there's still a problem. So how do we get asymptotic regularity? Where should we get it from if we only have a non-expansive operator? And maybe an intuition could come from the following case. Let's see it's the rotation around 0. So this is 0, and then if this here is xn, then the next xn plus 1 would be slightly rotated here, maybe xn plus 1. Maybe I should draw a larger rotation here, and also maybe I rotate to the right because there's no. So this is so it stays the same radius, but it's just getting rotated here. Xn plus 1 lies here. So what we see is we did not move any closer to the origin because we're just rotating. But if we have these two things here, we could consider the line connecting the two and place our next iteration. So this is not actually not txn plus, it's not xn plus 1, but it should be txn. So these two things are, this is not closer to the origin, but along the line, all the points along the line, they're actually closer to the origin. So let's just take some point here in the middle as xn plus 1. So a convex combination of xn and t of xn. This has moved closer to 0. And if we now again rotate that guy, maybe over here, txn plus 1, and take the connecting line and take this here as xn plus 2. So xn, t of xn, xn plus 1 in the middle, again rotating that around the origin, taking xn plus 2 in the middle between xn plus 2 and txn plus 2, we move close to the origin again. Okay, and this looks like a good idea, and in fact it's working. Oops. Okay. So this is now a theorem. So the previous theorem 25.4 was called Krasnodębski-Mann fixed point theorem, and this is now the Krasnodębski-Mann iteration. So again, T is a subset of X, non-empty, closed and convex. I think for the previous theorem maybe we did not even use closed and convex, but here we want to use it. T is a mapping from D into itself, non-expansive. And non-empty fixed point set. And then we need a sequence which does these convex combinations. So we call it lambda n, so it would be a sequence in 0, 1, such that and the condition is maybe a bit weird, but in the proof you see why you need it, that this sequence here, if you sum from n from 0 to infinity, lambda n times 1 minus lambda n, this should diverge, let's say, equals plus infinity. Okay, and we define the for some x0 in D, the iteration xn plus 1 is equal to xn plus lambda n txn minus xn. So, and this is this announced fixed convex combination of xn and txn. So, and then what do we have? Then we know that first is that xn is Fee monotone with respect to the fixed point set. That's already very good. And second, it's asymptotically regular. Okay, and third, this is a simple conclusion. Xn converges to some fixed point of t. Oops, fixed point should be. Okay, So this is a little less than we would get from Banach, of course, but for Banach you get unique fixed point and geometrically fast convergence towards a fixed point, and even error estimates. We don't get this, but we get at least still convergence to a fixed point. The very simple idea is to relax. This is called relaxation here. This thing here is called relaxation. Actually, I'm not really sure why it's called relaxation, but that's how it is. So don't go the full step. Okay, as we let us see, for some methods it's not relaxation is the right thing to do, but over relaxation, moving further in the direction where you come from. We've seen that already in the accelerated descent, but that's a slightly different technique here, because here you first do the step and then do the relaxation. Okay, good. So let's prove that. Okay, so first one thing is we already needed convexity to have the iterator well defined, right? We need that this convex combination stays inside the domain of T, but the domain of T is D, which is convex, so everything is fine. Okay, and now we take some fixed point. Y should be a fixed point of T. And we use the following equality, which looks wrong, but it's not actually. And the equality looks like if you have lambda u plus 1 minus lambda v squared plus lambda times 1 minus lambda norm u minus v squared, that's exactly equal lambda u squared plus 1 minus lambda v squared. I say it looks wrong because if you like, okay, just start simple and expand the square, but then you would get lambda squared here and 1 minus lambda squared over there, but you still have this term here, and if you just work everything out, this checks out, this equality here. So it's true, and you can just check it by calculating everything, and then it works out. Okay, so what do? We get xn plus 1 minus y. We would like to see that this is converging nicely. So now we plug in the definition of xn plus 1. This is that guy here. And moreover, we replace this y as lambda ny plus 1 minus lambda ny. Right? And then if we do that, we can kind of put everything together and would get 1 minus lambda n xn minus y plus lambda n txn minus y. So that's basically the trick already to get this convex combination in here in this square. And then we use this equality here and expand to 1 minus lambda n times this here xn minus y squared plus lambda n txn minus y squared minus lambda n 1 minus lambda n and txn minus xn squared. Yeah, and then we use non-expansiveness to estimate this guy here by xn, norm of xn minus yn squared. It's the same as this, and this lambda, just this 1 minus lambda n and lambda n add up to 1. So we get xn minus y squared minus this guy here, lambda n, 1 minus lambda n, txn minus xn squared. Okay, so what do we get? This here, we subtract something, so we get xn is Fee monotone with respect to fixed point set of T already. Okay, that's already good. We know a lot of stuff about the xn. It converges, yeah, a lot of stuff is already known. Not enough, but it's already something. If we apply this guy here recursively, we get, kind of move this here and then move your way back to x0, and then in the end remove this xn plus 1 minus y, you get that, and recursively you get that sum of n equals 0 to, say, sum everything up, let's say infinity already, lambda n, lambda n times 1 minus lambda n, then this norm here, txn minus xn squared, is smaller or equal to x0 minus y squared. Okay, so that's what you get if you apply this guy here recursively towards infinity somehow. And we move this kind of the limit of xn minus y. It exists, you don't know what it is, it exists. And it's non-negative, and we can remove it. So, but now comes the important thing. This guy here, no. We would like to know something about this, but we know that this series here, so since the series over lambda n, 1 minus lambda n, diverges, right? So, but now we see that if we multiply it with these numbers here, then it's going to converge. So without these numbers it's diverging, with these numbers it's converging. What does that tell us? They can't all be large. Some may be large, right? So every second or every third, or many of them may be large, but not all of these can be large. Otherwise, if they would be bounded from below, away from 0, this would not be true. So they can't be bounded from below, away from 0. So there has to be a subsequence of these terms which converge to 0. So I can say it does converge to 0. We can conclude that, but we can't say that it can't be larger than some positive epsilon. So what you have is that the lim inf of this term txn minus xn exists, of course, and it's 0. It has to be 0. Okay, so that's, again, it doesn't sound like much, right? We would like to have a little bit more. We would like to have that this is at least convergent, because we want to use these asymptotic regularity, because this would say just that, but we only have that the lim inf is 0. But now, we can show the following. But since, and so what we do is we take a look at, not at xn plus 1, but t xn plus 1 minus xn plus 1. This guy here is actually equal to, and again we plug in what we plug in, this one's so we replace xn by the iteration xn plus 1. And if we do that, we end up with txn plus 1 minus txn plus 1 minus lambda n times txn minus xn. Okay. So what did we use? We used the iteration in the form that oh sheesh. There's a typo, I guess. Okay. There's a typo. No. Sorry, I just, right now I don't see where this comes from. It has to come from the iteration, but I missed some point over here. Because this cancels with this maybe 2, but anyway, so let's assume that it's 2. I'm going to check, and if it's not true, I'm going to let you know. So now, next thing would be to use the triangle inequality and non-expansiveness. Triangle inequality is split in these two parts. non-expansiveness here, which gives us xn plus 1 minus xn, and then here it gives us 1 minus lambda n, and here txn minus xn. And then, oh sheesh, I always tend to forget all the arguments for the intermediate equalities, but this doesn't seem true. Just give me a second here. So maybe I just completed it there, and then the break which is coming up, I'm going to check, and then probably I can let you know what happens. So what's now here is that this should be xn txn minus x n, and then you show that it's decreasing. You see that it's decreasing from one step to another. The lim inf is actually 0, so the full sequence has to be 0. So has to converge to 0. So if we have the lim inf is 0 and the sequence is decreasing, then the full sequence has to converge, and the rest follows. So the claim follows by the previous theorem. So claim follows by the previous theorem 25.4. And so now it's time for the break, and I try to check what was behind these guys here, and in case I succeed, I tell you later. So, but now comes the break, and the break now features one of the new videos on studying math of economy and finance here at TU Braunschweig. Yeah, our students here worked hard to produce a very, very nice video showing prospective new students how it is to study math of economy and finance, so Finanz- und Wirtschaftsmathematik. So in case, just have a look. It's also on YouTube already since Friday, but in case you like it, you may just share it on social media or whatever, and so that we get all the people who would be interested in studying Finanz- und Wirtschaftsmathematik here at TU Braunschweig. Have fun.
Finanzen, Mathematik, Versicherung und Programmieren in einem Studiengang.
Wie das zusammenpasst und warum ihr euch für ein Studium der Finanz- und Wirtschaftsmathematik an der TU Braunschweig entscheiden solltet, das zeigen wir euch in diesem Video.
Hey, ich bin Laurenz und ich studiere gerade im 4. Semester.
Hi, ich bin Julia. Ich habe ja auch hier studiert und bin jetzt wissenschaftliche Mitarbeiterin an einem Institut.
Wir sind heute hier, um ein bisschen über unseren Studiengang zu quatschen. Wir sitzen gerade in der Hängematte. Das ist so der Raum, wo die Studis zwischen den Vorlesungen ein bisschen chillen. Wieso hast du dich eigentlich damals für deinen Studiengang entschieden?
Ich fand Mathe immer schon total cool und wollte dann irgendwas mit Mathe studieren. Und dann habe ich mir überlegt, dass die Verknüpfung mit Wirtschaft sicherlich spannend ist. Da hat man einfach total viele Möglichkeiten, was man damit machen kann.
Also ich könnte mir zum Beispiel später auch mal vorstellen, in einer Bank zu arbeiten, im Bereich der Risikobeurteilung oder auch bei einer Versicherung im Bereich der Unfallforschung.
Also mir hat während des Studiums das Halten von Tutorien total viel Spaß gemacht und deswegen habe ich mich für den Weg in die Lehre entschieden. Aber man kann zum Beispiel auch in Unternehmensberatung arbeiten oder in der Softwareentwicklung. Letztlich gibt es eigentlich in jedem größeren Unternehmen Aufgaben für uns.
Und das, was wir dafür brauchen, lernen wir hier an der TU, die mathematischen Grundlagen und logisch und strukturiert an Probleme heranzugehen.
Ja, und in den Wirtschaftsvorlesungen lernen wir die Grundlagen und Instrumente der Betriebs- und Volkswirtschaftslehre kennen.
Durch Übungsaufgaben wird die Theorie nochmal vertieft. Das kann man alleine oder auch mit Freunden machen. Mit Freunden macht es natürlich viel mehr Spaß und ist auch einfacher.
Zusammen mit Freunden in der Mensa oder Bibliothek zu arbeiten oder auch gemeinsam zu programmieren, hat mir immer mega viel Spaß gemacht.
Ich finde Programmieren auch echt cool. Da kann man das, was man in der Theorie gelernt hat, direkt in der Praxis umsetzen und weiß, wofür man es gelernt hat.
Was mir ja auch total gut gefällt, ist, dass man so einen engen Kontakt mit den Lehrenden hat. Mich hat es damals zum Beispiel überrascht, dass ich meine Studienplanung so genau mit meiner Professorin durchsprechen konnte. Gab es bei dir auch etwas, was dich so überrascht hat?
Ja, nach ein paar Wochen ist mir aufgefallen, dass es doch mehr Mathe ist, als ich anfänglich angenommen habe. Was ich aber überhaupt nicht schlimm finde und mittlerweile macht es mir echt total viel Spaß.
Und? Meint ihr, Finanz- und Wirtschaftsmathematik ist auch etwas für euch? Dann schaut doch in der Videobeschreibung vorbei. Dort findet ihr Links mit weiteren Informationen.
Bis bald und vielleicht sieht man sich ja mal.
Okay. Yeah, so at least This point here is actually clear, I guess. Just a second. There's no situation there. So this guy here, all this is inside here, is equal to txn plus 1. And then we have here txn negative, txn positive from the 1, which is gone. Then we have minus lambda n txn. And also we have minus 1 minus lambda n xn. Oh yeah, okay. And then we see that this is exactly txn plus 1 minus xn plus 1. It's just it was just plugging in the iteration. Okay, so sometimes I'm too blind. And then the rest is here clear. This is just non-expansiveness here. And triangle inequality. And then for the last step here, actually I don't see it yet. So that is now okay. Okay, so I'm stupid. This is just txn by, oh no, it's not. This would be from the previous one. So maybe, yeah, I'll check later. I suspect if we just plug in the same person again and check that it holds like this, but okay, I leave that open for later, and I'm going to check in quite a minute. Okay. So good. Anyway, sorry for the glitches here, but I think I can fix that. Everything okay. So now our status is as follows. We know the Carlson-Zelsky-Mann fixed point theorem. If we just iterate and have asymptotic regularity, we have convergence to a fixed point. And more practically, if we have a non-expansive operator and do the relaxed fixed point iteration, and this is called the relaxed Mann iteration actually, then we do converge. We have Fourier monotone, we have these differences go to 0, and then we have convergence towards the fixed point. Okay, so now what does that give us? What does that help us with the solution of monotone inclusions? There's one more notion which is would be important here. So of course we could apply this to the resolvent already. We know that the resolvent is non-expansive, and this would be fine, and we also know that fixed points of the resolvents are solutions of the inclusion. But things are a little bit better. Yeah, things are a little bit better. So for example, so maybe you could just check what does this condition here mean. So this condition here means that the so lambda n should be between 0 and 1. So but if it is 1, then the summand here is equal to 0. And if it would be 0, it would be 0 as well. And you see if lambda n comes too close to 1 or too close to 0 too often, the divergency would not hold anymore. So if the lambda n goes to 1, like 1 over n squared, for example, then this would be a convergent sequence. So it has to stay away from 0 and 1 all the time. So you really have to do relaxation. And this sometimes feels like, why should we really do it? Is it really helpful? So what we're going to see right now, there's a broader class of operators where this relaxation is indeed not needed and convergence follows immediately. And the definition is, I find it a bit strange that this should be an important notion, but it is. It's a notion of averaged operators. So if you have t subset of x, some alpha in between 0 and 1, and t from d to x is called alpha averaged. If T is actually equal to 1 minus alpha identity plus alpha r for some non-expansive r. And then the other notion is if T is alpha average for some alpha, then we call T just averaged without knowing the alpha. Okay, then, so this sounds like a little bit strange. So it's like, maybe it's relaxed by itself already. Anyway, but okay. So here's the proposition that firmly non-expansive operators are automatically averaged. So if T is firmly non-expansive, and we call that that is true for resolvents. Resolvents are not only non-expansive, they are even firmly non-expansive. So then T is 1/2 averaged. And that's actually immediate, so we don't have to prove anything. We can just cite the proposition 24.9, which said that R equal to 2 times T minus identity is non-expansive. This we proved in this proposition. If T is firmly non-expansive, then 2 times T minus identity is non-expansive. And if you just solve that for T, you see that T is equal to R plus identity times 1/2, and that's it. Okay, so averaged operators are a thing. Firmly non-expansive operators are averaged, but with constant 1/2. And now comes the theorem, which is a slightly strengthening of the previous convergence theorem. So the proposition, it's only called proposition for some reason, because I guess afterwards comes a better theorem. So if we now have alpha between 0 and 1, T, now we take x to x alpha averaged, for example, firmly non-expansive, with non-empty fixed point set. And now lambda n can now be a sequence between 0 and 1 over alpha, such that the sequence over lambda, the series over lambda n times 1, or 1 minus alpha times lambda n, and n again going from 0 to infinity, diverges. So you see the strengthening here, alpha is smaller than 1, so 1 minus 1 over alpha is larger than 1, and again also here make this a little bit smaller, so you allow lambda n, for example, to be exactly 1. If alpha is smaller than 1, lambda n could be exactly 1 all the time. And lambda n exactly 1 would be no relaxation at all. Okay, that's another typo because it's no D. So for, let's write it with x0 and x, we define the iteration as before. Xn plus 1 is equal to xn plus lambda n txn minus xn, or put differently, lambda txn plus 1 minus lambda n xn. And then it holds three things. Xn Fourier monotone with respect to the fixed point set. Second, it's asymptotically regular. And third, same xn converges to a fixed point of t. So alpha averageness helps us in that we can have a larger range for relaxation and even over relaxation. If this 1 over alpha is strictly larger than 1, which it is, we could make lambda n even strictly larger than 1, so we can over relax. And we'll see that sometimes this is really helpful. Okay, let's prove this here and see where this alpha averageness can help. So we know from alpha averageness that this t can be written as 1 minus alpha times I plus alpha times r. which means solving for r. This is we bring this. You solve for r, and we get this is exactly 1 minus 1 over alpha times identity plus 1 over alpha times r. Okay, and moreover, we have that tx equal x if and only if rx equals x. So the fixed point of the t and the r are exactly the same. Okay, now we set mu n equal to alpha times lambda n, and then we can rewrite the iteration which we have in t also in r. So if we do that, we get xn plus 1 is equal to, then it's xn plus lambda n, and then here I plug in this form. Oh no, what did I do? That's actually t. Oops, there's another typo of mine. Oh boy, I should have checked more thoroughly here, sorry. Okay, so I skipped this because it's a simple calculation, and what I wrote there was wrong actually in the lecture notes. So what we get here is if we rewrite this with respect to these r, this is exactly mu n. Oh boy, a lot of typos over here. It's exactly mu n times r xn minus xn. And what I've written in the lecture notes is actually wrong, but it's even simpler than it's in there. So I'm sorry. So this is then true if we replace this, but then we also have this mu n is always in the interval 0 and 1 because the lambda n goes up to 1 over alpha. Alpha times the lambda n goes up to 1. And we also have that the sequence here, mu n times 1 minus mu n diverges. And everything now follows from theorem 25.5. Let me see, hopefully I'm not off screen. No, things fine. Okay. So we just pull it back to, by averageness, we pull it back to a result on R, and it's just a different view. So it's just a rescaling of the relaxation parameter. Okay, good. And now, because we know now that firmly non-expansive operators are 1/2 averaged, everything is now fine, and we have our nice corollary on the convergence of Mann iterations, relaxed or not relaxed, or not relaxed ones, for firmly non-expansive operators. So if t from x to x is firmly non-expansive, has fixed points, so fixed points not 0, then the iterates xn plus 1 being equal to xn plus lambda n txn minus xn converge to a fixed point of t if the lambda is now in the interval from 0 to 2, and this is just because of 1/2 averageness, so 1 over 1/2 is 2, lambda n with lambda n times 2 minus lambda n divergent. And then in particular, the simple Mann iteration unrelaxed converge. So firm non-expansiveness is enough to prove to prove convergence of the simple fixed point iteration. So these are kind of slight generalizations of the Banach fixed point theorem, but without these generalizations we couldn't do anything here. And that the nice thing is, or not nice, is that these theorems here in this corollary is able to prove convergence without being able to quantify it exactly. So that sounds like a bad thing, because Banach gives you much more, but the good thing is it works under very low assumptions, and which are much more realistic in our context here. So having a contraction really, or constructing a contraction in our context of monotone operators, it's tough to, and often in many cases just impossible. But with these theorems, which is kind of very weak assumptions here, we can still get convergence at least, right? And so this is kind of, so these theorems, even though they appear weak because they only give you convergence and nothing special, so no more rates or anything, but it gives you convergence at least, so even in cases where you wouldn't probably not expect this. And here's a few propositions, two more, which will be helpful in the following. So one proposition is, and then that's for the lecture today. So proposition 2510 is if you have D non-empty, T from D to X non-expansive, and I think actually we probably already used it, or and alpha. Actually, I already used most of it, but anyway, and alpha b is in 1, 0. Then we have the following equivalent. So the following three things are equivalent. The first thing is T is alpha averaged. The second thing is 1 minus 1 over alpha identity plus 1 over alpha T is non-expansive. And this is actually, we already showed this. But there's a third thing. The third thing is for all x and y in D, it holds that the norm of T of x minus T of y squared is smaller or equal to x minus y squared plus 1 minus alpha over alpha. And then here we have identity minus T x minus identity minus T y squared. So you see it somehow quantify a little bit how much of a non-expansiveness you have. Okay. Okay, so so that 1 is equivalent to 2. It's basically straightforward. So if T is alpha average, then T is equal to 1 minus alpha identity plus alpha R, which is, we've seen it already, this R is then 1 over alpha T plus 1 minus 1 over alpha identity, and that's already it. So this is all we have to say, we can say about this. To show that 2 is equivalent to 3, we use again some elementary inequality about norms, which is 1 minus 1 over alpha u plus 1 over alpha v squared is the same as, and it's somehow more or less the same that we had. It's equal to 1 minus 1 over alpha u squared plus 1 over alpha v squared plus 1 minus alpha squared over alpha u minus v squared. And again, it's elementary but not obvious. It takes some time to expand everything, but it works. Okay, and with this we can write Rx minus Ry as, and now just plug it in. We have it. This R here is this guy, so we plug everything in and we get this is 1 minus 1 over alpha x minus y plus 1 over alpha tx minus ty, and we take squared norms, yes, of course, squared norms. Now we use this thingy here and get this is equal to 1 minus 1 over alpha x minus y squared plus 1 over alpha tx minus ty squared and minus typos again. Yeah, the typo is actually it's here. Yes, the typo is because it has to be like this. Sorry. So because here we would like to end up with 1 minus alpha over alpha squared. And here we would have then yeah, this minus this, which gives us identity minus tx minus identity minus ty squared. And since this is larger equal 0, you see that the assertion follows from here, right? You can just yeah. And also this is a plus, so this is a plus, so this is correct. These are pluses. Oh sheesh. Yeah. You just oh no. So I also have to check this one probably. I guess this is now from this follows the assertion, and I want to check. I guess it's right, but as always, I just currently I'm not able to see it, but I guess it's true. So the last thing I wanted to show you is about Lipschitz continuity. So if you have, so the following proposition says 2511, if the non-empty part of x and d from d to x is L Lipschitz with so really a contraction, then t is even L plus 1 over 2 averaged. And note that if L is smaller than 1, then L plus 1 over 2 is again smaller than 1. So in the proof is this is now again, hopefully this is, yeah, that's now simpler. You can just call this alpha here and check out what do you get for identity minus 1 over alpha 1 minus 1 over identity plus 1 over alpha t. And if you see what this 1 over alpha is here, you see that so with this alpha and calculating this stuff, you get this is L minus 1 over L plus 1 times identity plus 2 over L plus 1 times t. So and then this R is Lipschitz with constant. So just writing down what this means and looking over here, the Lipschitz constant is then the sum of these two things, because this is Lipschitz constant with constant 1. This is also Lipschitz constant with something smaller than 1, and you get that the Lipschitz constant is at most, which then gives you, this is 1 actually, right? If you bring it on the common denominator, it's L minus 1 plus 1 on top, and this is L plus 1 and it cancels out. So this shows R is non-expansive, and hence T is alpha averaged, and that's it. Okay, so we're a little bit ahead of our schedule, but that's fine because I have something to do with it. Sorry for all these inconveniences and the sloppy places. I'm going to check and update the lecture notes and probably going to upload it. But then, yeah, okay. Okay, thanks for listening, and just I keep you posted about the updates. Okay, and then next lecture is tomorrow, where we're going to analyze the proximal point algorithm, which is what we do. What is a kind of a general method. It's basically just iterating on the resolvents of a monotone operator, and then you're going to converge to a solution of the inclusion. And in the last lecture, in the last week of the term, we're going to see that this is actually really helpful to get kind of a flexible framework for deriving very large class of flexible and simple to implement methods for monotone inclusions, and in turn for convex optimization problems. Okay, thanks for listening, and see you tomorrow.